escuchar un poquito cortado.
¿Me escucha
Tuve
bien?
la que esté cortada.
¿Cómo me escuchas ahí,
Sí,
Verónica? ¿Bien?
te escucho muy bien.
Ok,
Sí.
perfecto.
Good evening.
Hi, Martin. Good to see you.
Yeah, yeah,
Good to
good.
see everyone. We have a good audience today, and a really good audience.
Hi, Marty.
Hi, Joey.
Hi, Hector. I think you can start on time.
Excellent. Okay, let me just back to my view. Hello, everyone. Good day, good afternoon, good morning, good night for all of you that are joining us today on this webinar. This is the third session of the 2023 International Online Seminar, which is put together by INBAR. And the topic of this year's seminar is bamboo, a very sustainable construction material. And in this session, we are particularly looking into pioneers that have taken bamboo beyond tradition. So we are looking at pioneering construction innovations in Latin America, and we have three guests today with us. Veronica, Romildo, and Carlos Rincon, who will be joining us. My name is Hector Archila, and I'm going to be moderating this session together with Pablo Jacome. So welcome, everyone. I don't know if Pablo, you want to say a few words before we start. Right, so let's give this session a start. Our first speaker for the day is Veronica. Veronica Maria Correa Giraldo. She's with us. Well, I'm speaking in English because I'm guessing most of the audience would be English speakers, so will understand. But I know that we have translation, so you can use that facility if you want to. So Veronica is a civil engineer from the National University of Colombia, which is actually my alma mater too. She did a master's degree in engineering at the National Autonomous University of Mexico. And she has a very, very long experience, 18 years of professional experience in structural building design. And she's been working on bamboo and wood for the last 10 years. She's founding partner of Caltia Engineering, a construction company in structural engineering and sustainable construction with more than 300 projects, about 360 projects really, that they have developed for various uses, of which 80 of them are specifically for or have involved bamboo as a construction material. She's also founding partner and director of Bamboo Terra, which is a technology-based bioconstruction company with 75 projects and more than 15,000 square meters of construction. So you might appreciate that Veronica has a huge experience in the area, and she will be telling us a little bit of that experience in the 30 minutes that we have. She's also co-author of a patent, which has been granted in 3 countries for a construction system with bamboo and 2 computer programs applied to structural design. And she has also collaborated in the translation of one of the recent ISOs that we developed as part of INBAR and the ISO Standardization Committee, which is ISO 22156. understand.
Hola.
Hi, Veronica. Are we back?
Okay, okay. Yes, I have a little technical problems, but now I am
I
ready.
think I have a technical problem also here, and my connection dropped. So I don't think we need to make many more introductions. So Veronica, please share your slides with us. Sorry, I'm going to start speaking in Spanish now because I know that Veronica is going to do her presentation in Spanish. So Veronica, por favor, comparte tus...
Veronica, you have the floor now, so could you please share the slides with us? As you know, we have 30 minutes scheduled for your presentation. Whenever there's only 2 minutes left, I'll let you know, just so you can start wrapping up with your presentation.
De acuerdo.
All right, then.
Dime si ya se está completamente.
Please let me know if you can see my full screen. Just give me a couple of minutes, just a second. We're still facing some technical issues here. Yes, we can see it now. Fantastic.
Bueno, pues buenos días a
All right.
todos.
Good morning, everybody.
INBAR por esta
And thank you so much, INBAR, for having me over. It's a pleasure being here.
Que sea de provecho para todos los
I hope that you can all take advantage of my presentation and use it. I would like to let you know, just like Hector mentioned, the work that I'm going to show you derives or is the result of all the years of experience that we've accrued. And basically, it's led by Bambuterra, which is my second company. It's a technology-based company that was founded 2 years ago, actually 10 years ago. And our objective is to use mainly bamboo, but also other nature-based materials by using vernacular techniques, but also with the development or adaptation of these materials in order to create high environmentally impacted solutions. And we've developed so far around 75 projects with 1,500 square feet built so far. And in addition, the consequences of this lead to the use of a lot of bamboo and the capture of around 160 tons of CO2. And we've also, as you heard before, developed a patent that has been used so far. So I'm going to show you the result of my experience. And we've imagined bamboo, the combs of bamboo, as systems that can lead to construction and avoid the excessive use of other techniques. So this project introduced us to this. So we produced this for a festival, and this is basically what we do. So we combine architecture and engineering, and we develop blueprints that allow us to design tailor-made connections that also help us with the building process. This also came from a static idea that was a beautiful one by using bamboo combs in the city of Mexico, where it was built. And for this, we had to create some special joint that, based on our practice, and of course, based on the information based on general engineering, well, we needed to survey these, to test this, and to produce precise engineering. But of course, this is part of the work we do. So this product, although very architectural, well, bamboo is part of the structural solutions, and we validated this, and this is found in one of the most important areas of Mexico. And this is applicable for the business world, where most of the things we can see are conventional materials, and this also fed our experience where many comps were required in order to develop this project in a short time. And this also helped us with the assembly. This is a very architectural use, but one that also helped us being trained in the logistics of pre-manufacturing. Another project that was very challenging for us, it also had an architectural use, but used a lot of bamboo in order to create this prefabricated plywood that covered over 6,400 meters of interior lining with this coverage. So we've also worked with housing solutions. This has been done from social housing to residential housing, and we've used prefabricated systems for this as well. This is just another example of one of the products that we are selling. These are the geodesic domes. This is done with bamboo, and this has some metal ends, and this enables us to generate some very effective solutions from a perspective of business processes. And these are some of the processes that we have currently in place. And this has been done with scale models. These are some bigger projects. And we have evolved with time until we have been able to manufacture these concepts and these projects for Mexico, but also for the rest of the world. And we believe that this is some of the experience that we've had so far. I would like now to get into the matter and share a specific project with you. This is a place that was built. This is a fairground that is currently being built in the city of Chilpancingo, which is the capital of the Guerrero state of Mexico. So this project is part of a national project for the renewal of public spaces in this country. And so far, there have been over 1,000 projects. A lot of money has been invested, and 4 of these projects have bamboo. 3 of them have been successful. 1 of them was not, unfortunately. Why wasn't this one successful? Well, the reason why, and something that's also worth mentioning, is to understand that some bamboo projects are successful while others are not. This was only based on prices, so there were different possibilities for obtaining providers, but we decided to go with the cheapest, and very frequently the cheapest is not the best, and the consequences of this led to a very poor material. And before the opening of the construction, this material was plagued with insects, and all of it had to be renewed and replaced. So this led to very poor reputation of bamboo. And well, all the work that we had done, all the work that we put whenever the standards are not covered, this leads to people deciding not to want bamboo, and this leads to a very negative burden because of the effort that we've all put and the efforts that we put towards the use of this material. This is a successful project so far. And I would also like to talk to you and let you know why we believe that this project is on the right path, even though it's not fully built so far. So let me tell you. So this is a render view of the fairground of the Chilpancingo city, and we can see that there's a square. Well, this is a bullfighting ring, which is also used for concerts and others. This is Palenque, where traditionally cockfighting takes place. We have these 2 pavilions are built of bamboo, and I will go in depth about them. So these are 2 identical structures. This is the theater of the village, where different plays are shown, and these are 2 made of bamboo. There's a combination in Palenque, and here we can see the galerías. These are all galleries, the eastern one, the western one, and they are also built with bamboo. But there are other buildings, or this one, this is a structure that is not made out of bamboo. However, the majority of the new ones include bamboo. This is about 8,400 meters of construction. This is a diagram of the project. The project was developed by a highly regarded institution in Mexico called MMX. The structural project for the buildings that can be shown on green, blue, orange, and red was developed by Calta Ingeniería, which is the office that I lead. And the building project for bamboo was developed by Bamboo Terra and is currently also being executed by Bamboo Terra. And the general management is in charge of the company that won the bidding contest for this, which is called ABA Gerencia de Proyectos. So let me set the context. I would like to show you the city of Chilpancingo. From a seismic perspective, we can see this strip in orange color is the most seismically active strip of the country. So this is an area where the tectonic plates meet and they go into the ocean. Thus, this is all highly seismic. So we are in one of the most actively seismic areas of the country. And speaking about hurricanes, the area of Chilpancingo, fortunately, sits on the inside of the Guerrero state and it has a mid-level risk. So it's in the transition between mid and moderate for the indirect risk or impact. Well, it has a high indirect impact and a mid-direct impact of hurricanes. Just a month ago, Hurricane Otis destroyed the city of Acapulco, which is just 1 hour away from Chilpancingo. So hurricanes can also have an important incidence in the city, as you can see. Now, in terms of bamboo, Mexico is a country with a lot of endemic bamboo. In this state, we can find a lot of bamboo, and there are also some introduced species. Let me show you all the bamboo found in our country. This is our commercial crops. We are speaking of about, well, 5,000 hectares of bamboo. So these are some very productive areas at the moment, but additional 15,000 hectares have been found. So we have around 20,000 hectares of bamboo crops, but we don't have an official inventory. It hasn't been done yet. And there are about 30 very high quality producers that distribute all along the country. And based on the calculations made, we've estimated that there is around 1 million combs per year. Yeah, so this is the level of supply that we can expect. Historically, bamboo has been widely used in Mexico. We can see this in vernacular architecture and also in historical documents. And some of the major challenges that bamboo construction faces in Mexico is about convincing the system. By the system, I'm speaking about the political system. In this case, we're talking about this project. This project is made with local resources. So there were 5 aspects that were considered for this project to be developed at this moment. The first thing that we took into consideration is that we have some prior successful projects of the construction of bamboo. So this is also a consequence because of everything good that has been done with bamboo around the world. Also, the openness of local Mexican architects who now believe that it's feasible to build large-scale projects with bamboo. There is enough bamboo in Mexico in order to provide in time whatever was required for this project. We didn't have the need of importing bamboo in order to execute this. In addition to this, we also wanted to showcase that we have local talent in order to build in the precise time and form. And also, it is important to mention that we wanted to build a project that is feasible, not only from a perspective of time, but also of structural safety and costs. So we acknowledge all the work that has been done in Mexico in the last few years, and we would like to thank that this is a growing sector. So I would like to congratulate all the colleagues who have contributed with positive inputs to the bamboo sector in Mexico. So this was the work we did, and this is the work done with any kind of a structure, either concrete or steel. So we developed some models in order to carry out a structural design that goes hand in hand with construction models that enable us to have a design of interference between different blueprints in order to properly design the joints and have workshop plans as the ones that I'm showing on screen. These blueprints enable us to make a difference between the different elements and create a proper dimension of the size of the elements, but also create a structural blueprints of this kind that specify the diameter, the amount of bamboo required for each one of the items, where mortar is required, where it's not, what are the joints like, and others. We also did the necessary validation test because this enabled joints to have a proper capacity for the provision of energy in the case of earthquakes or hurricanes, because this is a work carried out in a public space that follows the Mexican regulation that is considered of great importance. Therefore, these structures need to enable, in the case of any natural event, the possibility of this serving as refuge for the affected population. And of course, we needed to be very careful and include capacity curves for our joints, and through these have some direct data about the proposal of the connections or joints that we were using in this case. These are some. Okay, let me show you a quick video that showcases the evolution. We can see the single tension. This was, of course, carried out in a lab environment. So let me continue. So let me show you the structures, the pavilions that have an area that adds up to about 3,000 square meters. The construction time was 6 months. They were already built and delivered. And the first thing we did was manufacturing the main structures. And basically, this is what the building process looked like. After that, we installed the main structures. We started with columns. These were prefabricated, as we mentioned before, and then we assembled these frames, and we use a very simple scaffolding system and some specific systems that use very simple pulleys. Of course, if this would have been built with steel tubs, the building process wouldn't have been as easy or as economical. Further on, we were able to install these complementary events to enable the possibility of this, and we were able to create a very efficient system. But during the building process, as we didn't have any intermediate columns, we did have some effects of instability that we were able to counteract because of the construction strategy that we developed. And as part of this construction strategy, we also included some steel elements. However, they were minimal, but they enabled us to stabilize the building process of the bamboo structure that is found in almost all the ends and joints. But of course, when triangulating and closing all this triangulation, this becomes a very efficient system. And we use these 2 bamboo beams that led to a very proper contribution for the structural performance of these pavilions. This is a view from the inside. This is a construction model, and this is how it was finally achieved. So basically, this is what we designed, and what we thought, what we designed was what we built at the end. So we were able to make it. These are some details about the joints. We can see zooming into some of the important structural joints used in this case. And this is the finishing phase where we added the details. Of course, in this case, we can no longer see the part before, but we wanted to ensure a proper durability during the lifetime of the structure. The galleries are about 3,000 square meters long. The construction time is 5 months. We've currently progressed on 30%. We've done a lot of work with the prefabrication of the main structures, and we also used joints that include metal ends, and of course they very easily help us do the construction system. We also have some fasteners. We also use some fish melt in some cases, but we were able to reduce the use of the fish melts. And these are processes that make the construction a very long and slow process. This is how we installed the main structures. Here you can see that we have already mounted the main parts, and this is the current status of the western gallery of this project, and this is where we are now. So I would like to show you now. As of course this isn't fully built at the moment, we are waiting for this to arrive. This is where we want to be. So this is a very long gallery, but of course we've divided into more modules. And through this, we are able to have better isolation of the structure of this very, very long structure in order to be able to control the lateral deformations that may come up and make building processes much simpler. And of course, following the topography of the site, which has a certain slope. And of course, we use the stairs in order to solve this issue. So these are some of the details related to the joints. They are very precisely modeled. And as I said before, this building model enables the creation of workshop blueprints that have enough detail in order to pre-manufacture and be able to assemble this in a most efficient way. This includes some steel elements that enable the control of the seismic force. And I said before, we are talking about one of the most seismically active regions of the country. We expect about the gravity force, but horizontally, this is part of the seismic forces that affect constructions on this side. So if you ever go there, you'll be able to see how this looks. If you visit it, this is how you'll see it. This is the structural construction model. There's no architectural ambientation in this case because its goal is to solve the issues related to the processes. This is Palenque, and this is a hybrid construction made of bamboo and steel. Its area is about 1,600 meters, and it's 50% completed so far. So in this case, we combined bamboo and steel, as I said before, and because of this, we were able to reduce the number of columns required for the upper chords of the main frames. We're speaking about 25-meter frames, which are located in a compression ring towards the inner side. So we are creating a clear space without intermediate support of about 50 meters. And of course here, you can see some of the tubes we use. They are about 10 centimeters width, and they also use bamboo combs that are between 11 and 12 centimeters. And the diagonals are also made out of bamboo. Here on the inside, you can see how the bull ring looks like. This is safekeeping all the frames. There are 22 frames that make up the main system. And I would also like to show you at this moment a picture of the construction model, just so you can better understand what we are trying to achieve in this case. So the main system is made out of tubes of steel, and they have hybrid frames of bamboo that also uses steel elements that are connected one to each other. And then all these frames are found in the middle. As I mentioned before, these are some of the details of the construction of the steel structure. Let me skip ahead just so you can take a look at the bamboo structure we used. So of course, this is the frame which was divided into two sections. You'll be able to find that this is the connection between both frames. Why did we divide them? Well, this is part of the construction procedure that we use in order to avoid having other kind of structures. Each one of these frames weighs around 1 ton, and the assembly process will need a tower crane that will allow the hoisting of these frames in order to make this happen, as we can see it on screen now. I didn't say this before, but the two other structures are lined with mud, and this has been made with plywood. In this case, the lining is lighter, and it uses some prefabricated panels. They have been lightened too, and they facilitate the assembly process because they're panels, of course, as you know. So these are some of the details of the connections. So these are the prefabricated panels, as I mentioned before. So this is the inside of the structure. We are talking about 50 meters of a structure, and this is what we can see. So this is the theater. This is the smallest structure, but this is also the most complex one. If you take a look, you can see the curved elements, but this was part of the architecture conception that we transformed into straight elements because of the urgent needs for the delivery of this work. Now we are currently prefabricating this. This is one of the workshops where we've prefabricated this, and this is where we are adding some of the elements. And of course, we can see the construction model of the theater. And as you can see, there are no longer any curved elements. Everything is straight in this case. And you can also see the integration of some tubes made out of steel. And this is in order to comply with the needs, specifically from a seismic perspective for this structure. This is the most asymmetric of them all, and it also has a lining made out of shingles. This is a very heavy lining or cover, so it does require more complementary elements. In addition, all the cuts in this structure are straight, and this, of course, facilitates the building process for us. So this is the smallest structure of all. It has 600 square meters of a cover area. And these are some of the indicators and some of the results of the work that we've done. Of course, the carbon footprint is going to be very low versus other projects that are made with commercially available materials, and the social impact that we've achieved from a quality perspective. We've had the specialization of dedicated labor. Currently, we have leaders, we have builders who are now specialized in bamboo construction. Some of these workers have been working with us for many years, while others have worked with some other colleagues, and we call them because of the size of this project. And they've had between 6 and 7 years of experience in building with bamboo. But we've also trained around 60 people who didn't have any prior experience with bamboo building, but now they have this experience. So this means a lot of progress from the building bamboo sector in Mexico. In addition, we've acquired around 15,000 combs in Mexico from over 10 producers. And we've also created some technical documents focused on the creation of this. We're also going to write 2 articles related to the connection for seismic applications. And we also have a training plan for students and professionals, which is based on guided visits as well as the techniques guided to this work. We've been doing this with universities. This includes engineers, architects, and part of the construction guild. And this will help a lot of people to understand the construction process leading to the final process. We're also writing a book and a documentary course in order to be able to complement or foster beyond what we've done, the information that has been created on this project. So this is part of the technical team that worked on the design and construction, and we feel very, very proud of already delivering the first 2 structures. This is one of the 2 pavilions. This is a picture that was taken a couple of weeks ago. And well, Bamboterra, the name Bamboterra, on behalf of them, I would like to deeply thank not only the support of the team that has directly participated with us on this project. This includes the design team, the labor team, but also the guild, all the people that work with bamboo, because of this, we have a greater background in the world. And without this information, this process wouldn't have happened. And we feel very happy and proud of sharing this work with you. Thank you very much. This is our social media. This is our email. And if you have any doubts, if you have any questions, please reach out.
Héctor, no te estoy escuchando. Sé que estás hablando, pero no te estoy
I
escuchando.
can't hear you, Actor. It seems that you're talking.
Can you hear me now?
Yes.
Sorry about that. Sorry about that. Estaba diciendo que el trabajo de
I
Verónica es
was pointing out that Veronica's work is absolutely impressive, and I love to see the process that she has traveled and also the fact that she is involved with so many projects. So I'm sure that there will be many more questions regarding your project at the end. So let me tell you how this is going to work. We're going to listen to all 3 presentations from the experts, and at the end, we are going to hold a discussion panel. I would like to give the floor to Pablo. Pablo, now we cannot hear you. Pablo? Pablo, are you there? We can't hear you. Pablo, are you letting me know that I should continue?
Pablo, ¿te escuchamos?
Pablo, are you there?
Right. I'm gonna try and pick up from Pablo. We had agreed that he was going to take over from here, but I can do the introduction of our next speaker, Professor Romildo Toledo Filho, or Filho, we would say, I guess, in Portuguese. Romildo is a full professor of materials and structures at COPE Federal University of Rio de Janeiro in Brazil. He's a member of the World Academy of Sciences, that's TWAS. If you know that academy, you would be familiar with the TWAS acronym. He's member of the Brazilian Academy of Sciences, also member of the National Academy of Engineering. He's a researcher that is graded as 1A, and that's agreed by the Brazilian National Council for Scientific and Technological Development. And he's a senior scientist at the Rio de Janeiro state. So he's got a wealth of experience in research, and he has done amazing work on bamboo too. He's the CEO of the Science Park at UFRJ. He's the director of the Center for Brazil-China Cooperation for Climate Change and Energy Technology Innovation. And he's head of sustainability for the Center for Research and Education on environmentally friendly materials and technologies of the Federal University of Rio de Janeiro. He's vice president of the Brazilian Society of Non-Conventional Materials. That's NOGMAT, isn't it? Well, it's AMTENC, which has the non-conventional materials conferences, which are great. He has conducted extensive research on sustainable materials for construction, vegetable fiber reinforced cement composites, bamboo materials characterization, the use of bamboo in concrete, reinforcement, with other materials as wood also, and rice husk for bioconcrete. He has also done work on LCA, sugarcane bagasse, and mineral additives for concrete. So Professor Toledo has also, wow, he's written so many papers, 280 peer-reviewed journal papers, and loads of articles, technical articles published in conference proceedings. So I'll leave you with Professor Romildo, who is going to be talking about the potential use of bamboo reinforced bioconcrete materials and structural aspects. So Romildo, please take over.
Thank you very much for the introduction, Hector. Can I share my screen?
Please. We can see your PowerPoint, so if you could put it on presentation, we'll be able. Yeah, excellent. There you go.
Okay. Thank you very much, Hector, for the introduction. It's a big pleasure to be here with you, Pablo, Veronica, and Carlos Eduardo in this section. It's amazing the work that Veronica has just presented. It's really impressive, the nice application. I'm going to show you the potentiality of using bamboo strips as reinforcement in bioconcrete. So let me first of course, our group here in the Center for Sustainable Materials, we are, of course, focused mainly on sustainable construction, as you have mentioned, using different possibilities. The first one was the use of vegetable fiber as reinforcement, but then we did work a lot of work on bioashes as cement replacement as well. So this is very important to reduce the CO2 emissions of building materials, for material that is used in large scale. Now we are working with bamboo pole, and also is starting to develop here in Brazil bamboo laminated. So it's not industrialized yet. So we are developing solutions here in our lab. These materials, they find they are in accordance with many of the SDGs, so they can be also reused or even deconstructed. So deconstruction is something very, very interesting, and that we need to make the advantage of using bio-based materials to do that. So also we have here in developing country many kinds of biomass, bio-based materials. So this is very important that we develop the economy based on these materials. So from the solutions that we are studying here, the first one, as I said, was the use of vegetable fibers. In this case, the volume of bio-based material is not that high. Normally, we use short fibers or textile. So typically, the volume fraction range from 2 to 10%, no more than that. This is normal, the normal use we do. But recently, we started to use waste of agriculture, different kind of waste from agriculture. So waste from wood production, waste from husk production as well, both and sugarcane, the waste from electricity generation. So after the bioenergy is produced, so we have the ethanol and then bioelectricity, and the waste is rich in silica. Then we are using it as cement replacement. And these bioaggregates, we are replacing mineral aggregate to produce materials that are very rich in biomass. So we can reach up to 70% of biomass, and then we have materials that are good insulators, so materials that are lightweight. So there are many interesting applications for this kind of material. And in terms of bamboo, I'm going to show you here today more a system that we are developing now, that is the use of a strip of bamboo, reinforcing this bioconcrete. This system, again, it becomes feasible because the bioconcrete, as we use many biomass, the elastic modulus of this bioconcrete is in the range of 2 gigapascal. And the typical elastic modulus of bamboo strips is around 20. So we have, again, a rate of 10 times more stiffness in the reinforcement. This is more or less same thing as we have when we think about steel and more ordinary concrete, that we have, in this case, 210 gigapascal and 25 typically elastic modulus for concrete. So this is very promising, and this is the focus of my presentation today. We are not going to, I'm just giving an overview about the other topics that we are studying here, but we mainly discuss the mechanical behavior of bamboo segments, the effect of temperature. This is something that is very important to guarantee that in a system that can come up to 99% of biomass, that we can guarantee fire resistance as well. So I'm going to show you the characteristics of the strips of the reinforcement, then the production of the bioconcrete, and how we tailor the interface between the strips of bamboo and bioconcrete in order they can work well as a composite system. So this is very important. And then I will show you some results for the bending behavior of this composite bamboo bioconcrete, and then how the bioconcrete can protect the bamboo strips against fire. So just starting, bamboo is a functionally graded material. Normally, when we take the strips of bamboo closer to the outer side, we take it from a part where it has higher mechanical properties because it has higher fiber concentration, also has more hollow cellulose. The density is higher in the outer part of the bamboo. So bamboo is a naturally functionally graded material. So what we did here was to take strips from the part where we have a higher concentration of fibers, are typically around 55% of fibers in this region. Normally, the fibers are all aligned. And then in the inner part, the concentration decreased to 40%, and this changed the properties of the strip. Also, the presence of nodes also influence the response of this material under direct tension, under bending loads. So what we did here is when we see here that when we take the presence of nodes, in general, it reduces a bit the elastic modulus and the tensile strength of the bamboo strip, both when they are taken from the outer part and from the inner part. And those that are taken from the outer part has about 20-25% more strength because it has more reinforcement. So the influence of the number of nodes, the nodes works like natural defects when we have this because we have disalignment of fibers in this region. So when we put it under direct tension, the influence of one or two nodes, we did the test also in longer strips because this is how we are going to use. Normally it is going to have many nodes along the strip when we think about a structural use. And we did here a test with no nodes, so just using the internodal length, and then with one node in the center, and then with two nodes. And what we saw here was that there is a slight decrease when we go from 1 to 2 nodes. But the main reduction is with the presence of one possible source of defect where we initiate the failure. In terms of the temperature effects on the mechanical behavior of bamboo, we did first a thermogravimetric analysis to show the stability of bamboo. Normally, bamboo, when we dry it up to 100, 150 C, we lose only moisture. After that, after 160, if you see here from the thermogravimetric mass loss curve, we see that from that point, some active pyrolysis stage starts. So we start to decompose hemicellulose, cellulose, and lignin. And this process is nearly complete when we are in temperature in the range of 380 C. So, but intensive mass loss starts from about 250 C. So what we did here was to take some of these strips and we put in an oven. Samples were all of them in the equilibrium humidity when we started that, so humidity wasn't a variable. And we did different residence time and different temperatures from 100 C, 150, 200, and 250 C to see the response of these materials when we increase the load and also the residence time. And then we did the test afterward in a 300 millimeters freeze pump using clip gauge to detect the extension and calculate the elastic modulus as well. So this is the variable, it's 5 curves. The one in black is a more typical response. So this is non-heated sample, so the reference one. When we start to increase for different times when increase the time of the residence time up to 100 C, it only is dry better, so it doesn't change much. It's even increase a little bit the elastic modulus of the material. But when we go to 150, until 150, this is benefit. We have benefits from this behavior. Of course, when we go to 200, then the mass loss of the lignin and also of the cellulosic material start to happen, and we have at 250 a strong decrease both in strength and also strain capacity and elastic modulus. So we see here in these graphs that up to 100, 125, 150, even 150, we keep very much the ultimate tensile strength, so it's nearly the same. But after 150, and mainly after in the range of 200, 250, the reduction is quite expressive. So it can, when we normalize it, as we can see in the bottom of the last graph, we keep only about 20 to 30% of the strength, depending on the residence time. When we leave it for a longer time, we even lose more strength. And this is mainly because of the decomposition of the material became like the filaments are not together anymore. So the stress transfer cannot be made. So the materials work like when we break one filament, one fiber of bamboo, then the process of fracture starts. And that's the main mechanism of the failure pattern. So this is the loss of the adhesion materials between the filaments of the fiber bundle of bamboo. We also did this test the transverse direction. So it was just to give an idea about the tensile strength when we test it in the direction where we have nearly no fiber. So this is the matrix strength, and we have only 5%, but the mechanism is the same. The matrix is mainly lignin and pectin, and also after 150 C, we start to see a strong decrease in strength. But of course, if we compare the transverse tensile strength with the direct tensile strength, it's about 30 times less in the transverse direction. So the idea of using the bamboo as aggregate was also because when we start to study the lamination or even the combs, we lose a lot of parts of the comb, between 40 and 55% sometimes is lost. And what we did was to crush it to produce bioaggregate by crushing. So it's an industrial mill. And then we produce a kind of fibrous material that we classify, so the fine part and the coarser particle, but it has always, the morphology is always elongated fiber. So we have about 8 to 10 times aspect ratio. So it's the length of this crushed comb has about 8 times more. They are longer than the cross-section dimension, typical cross-section dimension. If we grind a lot, it's more circular, but otherwise it has like a 2D cross-section. And the density of this material is around 600 kilograms per cubic meter. We also determine the water absorption because we need to, in the mix design, to compensate this water. The destructives that comes with bamboo to affect the hydration of the cementitious matrix, it can give a certain effect of delaying effect in the hydration. So we study this washing this material or doing some filtration using nano filters, and we did also the use of some chlorides to increase the velocity, to recover the velocity of the hydration reaction. But bamboo is not a big problem, but it has some delay. We see here if no treatment is given, the hydration is delayed by 1-2 hours, and also the peak of the heat of hydration is also reduced. Then when we use filtered water, doing any of these nanofiltration or osmosis reverse, we can solve this problem, bringing the material very much the same performance, or even better when we use some accelerators than the normal cement matrix. You see here how is the rheology of this material. So we can have a material that has good flowability, so it can spread, it can fill the molds without segregation. So we have a material like that can have up to 7% of biomass in the composition. We also replaced a lot of cement. So in some mix, we had 7% cement replacement. This is done in order we can reduce the emissions of the cement, because then we use pozzolanic materials. Both materials we use from bioash, we are using rice husk ash or metakaolin to replace cement in this proportion. But we see here that a good compromise is already obtained when we replace between 40 to 50% of cement by supplementary cementitious materials. In this case, we keep the elastic modulus in the range of 2 gigapascal, compressive strength in the range of 15 MPa, using 40% of biomass. If we reduce the content of biomass to 35 or of 25%, we can come up to 20 MPa compressive strength, and we can have elastic modulus in the range of 6 to 7 GPa. So we also did the test under indirect tension to see the fracture energy of this material, and this also to determine the bridge effect that these filaments can promote here. And we see the post-cracking zone, the effect of the bamboo filaments working to control the crack opening under indirect tension and also under direct tension. So the tensile strength, it can be in the range of 1 MPa, and under indirect loads, it can go up to 1.5 MPa. A very interesting property of this material is that we can start to have low density material. So you see the density here can be as low as 750 kilogram per cubic meter, and then the thermal conductivity is quite low, what can be good also for the thermal efficiency of buildings using these materials. We are now studying the use of ultralight materials. So the density here is in the range of 120 to 100 kilogram per cubic meter. Then in this case, these materials can be used as isolator and also to produce a sandwich system using outer layers with textile or short fiber reinforced cement matrix as well. So we can produce sandwich panels and then develop construction systems using these materials. Coming to the use of segments as reinforcement of bioconcrete now. So the first test we did was the bonding. Normally the pull out of these strips from the bioconcrete, it can be very low if we do not use any kind of polymeric coating, so we are using both a natural biopolymer as coating, and also a castor oil biopolymer, and also a commercial epoxy resin. And we also saw the influence of using sand, fine or coarse sand, to improve the roughness and the adhesion between the two materials. So it's a very critical part, the stress transfer. And then we see here, when we do not have any kind of treatment, the pull-out force is relatively low. We do not mobilize much frictional loads during the pulling out process, but just using some polymer. This is the use of commercial polymer, epoxy-based polymer, and then we more than double already the pull-out force, and the energy is also much higher. And then when we use sand, the behavior is 4 times better than the reference one, the non-treated one. Then we have much higher load, and also the displacement up to this load is quite stiff. The curve, what shows that we can control the cracking process development in the composite system. So there is no much difference in using fine or coarse sand. Both behaves well. Then we did some, already coming to the structural behavior, we did some tension stiffening test. So we put one layer, one strip of bamboo inside the bioconcrete, and then we tensioning the element, and then we see the crack formation. So this give us the tension effect mechanism. So you see here that when we put in bioconcrete from 25 to 45% of biomass, it doesn't change much, but mainly all of them shows very fine cracks, very well distributed cracking process. You observing the 4 phases of the element. So this brings us to the last part of this of the structural application, that is the use of untreated and treated reinforcement, now using a number of strips as reinforcement. So we put here in this along the height, in the back of the sample, we put the 3 strips of bamboo, then the bioconcrete, and then we test them under bending. So we see here that when we do not have any reinforcement, so this is just the matrix, the material is quite brittle, just post-cracking failure, just the energy that is given by the small particles of bamboo. But then when we have this strip, even untreated, it can more than double and give very high energy already, but the behavior is much better when we use the treated sample. Again, here we have a very nice response, what give us optimism to design these materials for many possibilities of structural systems, building systems. And you see here the failure mode, when we do not have any just the fibers in the bioconcrete, it has the bridging effect is quite reduced. We form only one crack. When we have untreated bamboo, we have some slip between the bamboo and the bioconcrete at late stage of the bending process. But when we use the treated segments, you see here a multiple cracking formation with controlled cracking process. So this give us really a very optimistic view of the use of this system of bamboo as reinforcement of bioconcrete. So in terms of fire reaction, we use the cone calorimetry test. We did both ways, using also the effect of the bamboo being a functionally graded materials. Sometimes we expose the internal part or external part to the radiant flux, and then we see how this material behave under this heat. So after a certain time, the bamboo ignites, so it gets flammability. So both when the inner or the outer part is exposed to the radiant flux. So these materials also, we get many properties from this test, but the most important I put here, so it's the heat release rate. This is very important. So if the material release the rate very fast, so it goes, the time to ignite is low. So we should all, of course, protect this material with a layer of some fire retardant. In our case, as this bamboo is going to be used inside bioconcrete, we did a study to see the effect of the covering layer, so of the strips, to see the minimum covering we need to have to protect the system. The inorganic matrix, it's already protects the biomass itself from the flux, even using up to 85% of biomass. The inorganic binding can protect against the flammability. So using these three lengths, 7, 11, and 15 millimeters, we did the test. So this is the heat release curve with time, just for the bamboo strips. And then with the bioconcrete, we see here that for the bioconcrete, very low heat release is observed. This is mainly from the small particles of bamboo that is in the surface of the radiant flux. But then when we use 7 millimeters, and 11, we see here that 11 millimeters retards a lot the liberation of heat, but it comes after 1,200 seconds. So it reduces the heat release, but doesn't reduce completely the ignition of the bamboo. So 7 and 11 millimeters is not enough to protect completely the bamboo against ignition. But with 15 millimeters, it's very much the same behavior as the bamboo bioconcrete. So we see here with this strip is very fast, the heat release, so it's quite quick, the process. And then with bamboo, it's very low, it's low, and then 7 millimeter, 11, and 15. With 15, we come back nearly to the same situation where we have no strips of bamboo. So protection is total. See we here the total mass loss.
Sorry, Romildo, you have a minute.
Yeah,
sorry, Romildo, sorry for interrupting. Yeah, please. Yeah, thank you.
Yeah. So this shows the difference between the bamboo and the strip itself, and then it shows us just a picture here. When we have the 15 millimeters, the bamboo remains very much with the same. Then we put just to see the thermocouples, to see the temperature close here, and then we see that when we have 15 millimeters, the temperature that reach the bamboo is between 105 and 107. That we saw already, that is enough to keep the properties of the material. So to conclude, just in the last minute, Hector, we see that it has we need to assure a proper adhesion, and that using resin can be a good way to improve that, especially when we put some sand together. Good structural performance with multiple crack formation can be observed. And of course, with 15 millimeters of covering, we protect the material completely against fire. Now we are working with life cycle assessment and BEAM to design optimized, low emission and energy efficient systems. So this is part of the group. Part of this group is working in this subject, but many of the others are working in the other topics I mentioned before. Thank you very much, and it was a pleasure to show the results we are developing here in our group. Thank you very much.
Thank you very much, Professor Romildo. It's very, very interesting. I hope we have enough time at the end because I got many questions because we've been doing some work also on reinforced bamboo reinforced concrete. So I'll pass over now to my colleague Pablo. I hope his problems with the mic are all solved.
Aló, aló, ¿sí? Héctor, ¿me
Hola, Pablo.
escuchan? Hola.
Sí, perfecto.
Bueno,
Muchas gracias.
Well, can you hear me now? Fantastic. Good morning, everybody. Good afternoon. Good evening for everyone who are participating. I apologize for the previous presentation. We were experiencing some technical issues. However, I'm back here. These have been two fantastic presentations by Veronica and Romildo. I believe that this clearly shows all the good work that is being performed in Latin America. And that's the reason why the use of bamboo for constructions increases and it becomes very well positioned. I would like to send you my regards. I'm in Sao Paulo. I'm very close to Romildo. Here in Sao Paulo, we can see a lot of things that we want to work on and that we want to continue fostering in matters of construction. Let us continue now with Carlos Eduardo Rincon, who's going to speak about sustainable bamboo construction inspired in vernacular techniques. It's a great pleasure and honor to have you, Carlos, with us during this session. Carlos had the chance to share some time with us at the regional office. He's a fantastic professional. He's a Colombian architect from the Javeriana Pontifical University and a specialist in education and human development. He has a master's in habitat and a PhD in environmental sciences from the Pereira Technological University. He's an associate professor of the engineering and processes and member of the working group in cleaner production of the University of Pereira. He coordinates the line of sustainable construction. His PhD research is about resilience sustainability of vernacular architecture. This is the case of the architecture of Huaduan Bareque, the cultural landscape of Colombia. Welcome, Carlos, and please, you have the floor. Go ahead with your presentation. Thank you very much. Thanks, Pablo. Greetings, everybody. I am very happy for being here in this event. Thanks, INBAR, for the invite. I would like to let you know if you can hear me well. Yes, we hear you well. Yes, we hear you well. That's fantastic. All right, so my presentation is already up there. Can you see it? Yes, it's loading. I think it's up now. All right. So, with no further ado, just like Pablo mentioned, part of my presentation today is based on my PhD thesis. And this one was focused on the coffee landscape of Colombia, this in the center-west of our country. And just to show you one of the concepts, I'd like to start by letting you know that the concept of resilience shows a scheme where we can see what happens when a system, in this case, a technical system, such as housing, made out of bareque, is faced with a disturbance. Well, two things can happen: either an adaptation process, which leads to changes in the system, or otherwise a transformation whenever the impact is too big. Just a second. I was trying to use the pointer, but it doesn't seem to be working. But either way, we can see your mouse arrow, Carlos, so that's good enough. All right, so I'll do it with my mouse. Fantastic. So this is a picture which basically showcases what the social construction of the technology of Bareki has been for the cultural landscape of the coffee area of Colombia. So at first, we can see some building systems that were done in the Iberian Peninsula and Spain. These are medieval structures, they're simpler. These are how houses were built. And of course, in our case, we had pre-Columbian bareque or bamboo. So here we can see some pictures that show that the word bareque is a pre-Columbian one. And this relates to bohío, which is usually what we understand as these houses, these huts. However, the term hut or dot hut has a kind of resemblance to a word that we don't like to use. So this showcases how this was built with bamboo, with cane, with pieces of wood, and how this weaving creates bareque, right? So because of hybrids on pre-Hispanic and Spanish typologies, we created the first typology called Rancho de la Tierra. But of course, there's also the tapia española, which is the Spanish wall that was used. So we changed the way of using this. The pre-Hispanic case that had rectangular shapes or square shapes that belong to a Western point of view. So these typologies, in this case, we can see a house in Cocora, in Quindío. This is one of the best well-known places of this landscape. And we have the national palm trees in this case. And basically, this is a very simple construction system where 4 posts are placed on the ground. Then we build a door and we create the cover for it. Okay, let me go back now. So after this, the foundation bareque technique was created, and the innovation in this case is using a foundation that enables wood or wadua not to be anchored to the ground, so there wear and tear decreases. And this is a picture of the plaza. This is a very old picture where we can see the houses made out of this. So after this, we can see other disturbances. In this case, we have earthquakes at the end of the 1950s. We had some strong earthquakes in the country and especially in the coffee axis. So we created the seismic style, and this trembling bareque basically combines 2 parts. So we have tapia pisada on the first floor, and on the second one we have bareque. So this is the response to a condition of the ground. And then this kind of bareque started being used, and we use resources available. So because of this, we can consider other typologies. These are not the recurrent typologies. So we have this typology, and we use different kinds of bareque. We use this piece of wood, we use this other one, and this one that was even used in the Cathedral of Columbia. So after another disturbance, which is fires, we created the cement bareque that included the first instance of recovering the material. But there was a style process that included fashion innovation with the influence of the so-called Republican architecture. So walls are no longer made of what they were in the past, they're no longer made of soil, but there's also the use of cement in this case. And with this, we are able to answer to the prior two elements, but there's also a regression species, which is intervened bracket, because this also combines some unwanted techniques. So for example, there are doors made of concrete or the facade is made out of brick. And for example, in this case, we can see that this one has wings and this one has an attic. So here we're combining these two. We can show this technique, but whenever there's an earthquake, as the material is different, well, there is an issue, right? Because this structure can be done with bareque, and it can be anchored to it. And as I said, this is unwanted. So let us continue. The popular tradition in time, this happened between 1930 and 1945, where invasion bareque was utilized, and this is done in the periphery of the cities. So this was made in Colombia. So because of this, there was an improper image of Wadua, of architecture and construction for the poor. So this showcases that this material is very adaptable. So we need to take this back. So there's a stigma. So this is a contemporary architecture that looks better and that has a more aesthetic perspective. So this includes cemented bareque, and this includes a mixtures of different typologies. And this contemporary bareque has been seen recently. Sorry. This is because of the earthquake. This happened in 1999. So people realized that bareque houses 1 and 2 stories high had a very good behavior. Well, other type of houses weren't as good. So they started requesting the use of bareque, and when rebuilding the city, well, there was a decree issued and it was added to the construction code, and this includes the regulation for building houses with cement and bareque. So with this technology, a recent project that we were able to do with some Swiss cooperation resources and with the cooperation of FEDEWADUA, which is the guild of Wadua in Colombia. There are people associated to this in other parts of the world. So different designs and different actions were created in order to strengthen the value chain. So we had other allies in this case, including INBAR. And one of the products was the creation of studies for creating housing with bareque. And finally, a prototype was built at the Theological University of Pereira, and it's known as La Casa Campesina, so a peasant house. And this is a render view of the house itself. This is done together with a different building. This was done later on, and this somehow emulates the expectations in these farms. We also introduced some specifics, for example, the possibility of adapting to other conditions and preferences of the user. It was enabled by the Ministry of Agriculture, and we proposed a relatively simple system called Tangrama, so that people could use available spaces in order to determine these houses. And there were also studies carried out for the management of this. And here we can see the variable for the studies of wind, the sun effect, and also the percentages of natural lighting. So this is of course related to this being sustainable. And this answers to a current perspective of learning about vernacular architecture. This is a 3-year research done in Europe. It's called Versus, and this is an important reference where we are able to understand when deriving knowledge from vernacular architecture, this can also be used in neo-vernacular or contemporary architecture. These are the structural blueprints of the house. We can see the presence of biomaterials as wadua and others. And in the case of Colombia, this is very particular because we don't use raw material because there has always been a recovery over this. So this is done and we widen the walls and we do this for the community. This is of course covered with lime, and this is related to the stigma that I mentioned before, where we try to cover what is not considered the so-called noble materials as the stone or others. This is part of the building sequence, and we would like to show it because you will not be able to see it later when we see the finishing, but only on the structures. So here we can see how this was covered with cane. They call this esterilla in Colombia and caña picada in Ecuador. So here we can see the mortar that is placed on the coup, and we can see this hexagonal steel mesh and also the widening, and this was done with lime. And of course, this is a panoramic look of how this house looks. As you can see in the corridor, we wanted the water to be visible. This is specifically in order to showcase that we are using it intentionally. Also here, we left these windows because of our weather that requires this recovery. So we kept this. This is also done with wadua. And some of the main structures is made with wadua, while the doors are made with pine. And this space is called a witness, and this shows all the building sequence that led to this, so that this product, well, is one where students come to. It also includes decision makers, and this allows them to feel, to go through, and to value these vernacular techniques used in this case. So part of the work that we did on the Fedewadua project, which was systematized in one of the chapters of my thesis, is a comparison of the carbon footprint by using a life cycle analysis. This is the life cycle analysis methodology that I'm going to share with you right away. So in this case, we carried out a comparative study considering a typology of conventional housing, which we can see on the left. And this is made with clay bricks. So this is an urban house. And until 2015, these houses were built in the place where we're building, and they use the same materials. So here we put together the analysis for this. So this is the sequence for our methodology, the definition of the goal and the scope, the analysis of the inventory, the impact assessment, the interpretation of the results, and of course, in this case, we used OpenLSA as well as the EcoInvent databases. So in this sequence, we included production stages, we included the construction process, and these of course follow the prior SEA analysis, which was one of our advisors for the framework of the FEDEWADWA project with the Swiss cooperation. Of course, we wanted to facilitate the cooperation with other studies. So we calculate the distances. So one of the elements that usually impact the life cycle and the carbon footprint is transportation, right? So in this case, by determining the distances of the production of steel and cement, as well as the river materials, and also Wadwa, which in this case was estimated was brought from Quindío, which is a department close to where we are. So it's between Pereira and Armenia, which are the capital cities. And clay brick was brought from a place nearby in the municipality of Pereira. So finally, these were the estimates according to the work done by the two typologies for each one of the houses, the one made out of clay and the one made out of wadwa. And these are the emissions equivalent per each one. So for the clay house, we have 12,000 kilograms, but the area is not smaller. And in the Bareque house, we're speaking only about 7,000 of CO2. This is for all the house, and of course it's bigger. So we don't need any normalization in order to transform this. So when making the conversion, this becomes this part, and in the case of the Bareque house, it is 119 kilograms of equivalent CO2. So this is how things work. So the carbon footprint of the Bareque house is around 40% only. So in this case, we believe that this is not only sustainable building, but of course the calculations show this. So in addition, we included CO2 captured during the growing process. So the table includes the amounts of wadwa that was used and all the amounts that were used in the house. So we converted this based on some studies carried out by Professor Camargo, who's part of our university, who has systematically studied how this process is carried out. So this is what we took into consideration, and our calculation reached 11.88 kilograms of CO2, which are equivalent per square meter in the case of the Bareque house. So when doing this comparison and seeing the CO2 footprint, we can see how 119 reduces to 107. And of course, in this case, we are not contemplating the 11.8 kilograms of CO2 that were used in this case. So basically, this is what this is showing, and we can clearly see that neo-vernacular architecture, that contemporary architecture is indeed efficient. These are some of the results when analyzing the differences versus industrialized materials with the use of the structural system, which once again confirms the efficiency surrounding this. In parallel, beyond the comparison that I mentioned, because of the time, I'm not going to be showing the methodology now, but we did do a different kind of analysis with a green stamp, and this has become very important in Colombia. It's called ASH, because this is financed or enabled by the World Bank. So national banking provides some favorable conditions for those implementing this. So we can see with this green stamp what the efficiency looks like. We expect a reduction versus the baseline, which is basically conventional construction. So in the case of energy efficiency, we can reach 16.4% in energy savings. And in water, we're just above the survival levels, and this is because we're now using sanitary treatment devices, and this could be managed better with the management of rainwater whenever this could be used when the levels of technological maturity are higher. And this is one of the most relevant aspects of it that relates to the energy efficiency of the material. We're speaking about 73.707% of energy savings that are included in the material. So this means that this is the calculation for the Bareque house, and this is the case of a conventional house. So even though the system has been criticized because it's a black box system, as it calculates using its own parameters, I do believe that, at least for us, it is significant, and we need to mention that it harmonizes the analysis of the life cycle based on energy saving included in the materials. So here we can see some prototypes that have been recently developed. So there is an ever-growing interest by decision makers. On the left, we can see a prototype that is financed and sponsored by the Sustainable Development Housing, and the one on the left has been financed by the government of Caldas, and we've had some participation in these cases. So on the one hand, we are able to realize that we don't want to have a single typology where everything repeats, but we want to have some exploration capabilities that we can see this in time. In addition, there are laws or standards in place that have been created. For example, a housing and habitat policy that includes cultural housing. So this is an interesting message for other places. I've only seen this in Colombia, and it's not only about social housing, but also about cultural housing. So this is architecture that responds to the conditions of the environment using local techniques, and this is specifically what this housing neo-vernacular typologies are showing us. This is what they are trying to do. So it's interesting to take a look and see how this has progressed. In addition, we have the Wadwa law in Colombia, which encourages construction with Wadwan bamboo. And basically, one of the articles states that we have a very interesting goal, that we believe that if this is properly managed by the state and the different stakeholders, will eventually foster the efficient use of bamboo that would be very convenient for users. And of course, this will be done with Wadwan Bareque. And the goal is that new houses should be made with subsidies of the state, and at least 30% of them should be built with wadwa or bamboo. Even though we are aware that there is international development in the use of bamboo and wadwa in the coffee axis of Colombia, there are other regions that have other kinds of bamboo and wadwa. So we have a very interesting field, and of course in other countries we can also replicate this. So my regards to those who helped me at the different moments. And these are some of my bibliographic references, and I think that's all from my side. I don't know how we did time-wise. Hector, Pablo, what do you think? Well, thank you very much, Carlos. We are on time. You've done well. And I would like to thank you for the fantastic experience that you've shared with us. Now we have everyone listening to us, so thank you. Now we're going to have a Q&A session. Hector, are you there? So that we can start with the questions.
Hola, Pablo. Sí, sí.
Yes, Pablo, I'm here. Please go ahead.
Sí, sí, tengo varias preguntas, pues.
Yes, I do have several questions. Do you have a list? If you have a list, just let me know. Okay, so there's a question for Veronica. Please, Ronildo and Veronica and Carlos, please turn on your cameras so that we can take a look at the questions. Okay, so there's a question here. I know that Veronica has tried to answer some of them on the chat, but here the question is the immunization method that you use for protecting bamboo against weather in all these major works. What's the one that you use? Do you have an explanation about this? It would be very interesting to listen to this, Veronica. Please, you have the floor. Thanks, Pablo. Great to have you here. So immunization. The most accessible perspective for immunization in Mexico that producers have at hand locally is the preservation with bore salts and immersion. So this is what we're currently using for the structures that I mentioned. It is important to understand that all these structures include elements that are isolated from the ground and that have a lining. So we're using a design method that implies protection. But for other structures, for example, there was a facade at the beginning of my presentation where bamboo is completely exposed to UV light and also rain. So in this case, we use an autoclave treated bamboo with copper salts. So with this, we are able to increase the durability of bamboo, and this method is frequently used with softwood that are kept outside. Fantastic, great answer. Thank you so much, Veronica. I would like to give you the floor now, Hector. Fantastic. So we have another question in this case. This one is about corrosion challenges when working with bamboo. So, Veronica, you mentioned that bamboo and steel in Mexico, well, you've said that these projects are near the coast. So, how do you address these challenges? Well, this is one of the most difficult things to deal with. So we're using a resource where we combined steel and bamboo. We are near the coast, but we are about 100 kilometers away. So this is about, so yeah, we're not directly on the saline environment. So we used all these connectors and we used stainless steel, which lasts longer in the long term. And of course, this is all made with stainless steel, and all the plates have some primary paint and also an additional one that I forgot. It's called electrostatic paint. So they're all painted with electrostatic paint. That's why they're used for the automotive industry, and they're very resistant against the elements. Now, for the bigger elements, where electrostatic paint and the treatment of it wasn't available because of the size of the elements, we use conventional paint, but it was the best one available. Great, fantastic, Veronica. I have a lot more questions, but I would like to also allow Romildo to answer some of the questions that are related from my side too. So
are you on the call? I don't see.
I'm
Yes,
here.
he's there. He's there.
Oh yeah, you're there. Excellent, perfect. Romildo, I'm very impressed with the work that you have done, because it's, if there is, you have shown research, a very rigorous research method. You have gone through, the micro characterization of the properties of the material, and gone all the way through to fire, which is something that we don't do much on bamboo. And I congratulate you for that amazing work. So, but something, because we with Edwin and other experts, which we are all part of in the task in INBAR task force for bamboo construction. We have done some work also on the sort of looking at reviewing the reinforcement of bamboo, or reinforcement of concrete using bamboo. And I can see that, well, first thing, you're using thermally treated bamboo. And so I got a few questions on that treatment, because I can see also that when you increase the temperature, of course, your material becomes more brittle, and it breaks. It's more ready. It breaks more readily. So the first question would be, what was the sweet spot in terms of the temperature? What was the first? That was the first question. That's the first question. What's the temperature that is the appropriate one that you found to find a good flexible material, or material that keeps that elasticity, if we can name it like that. And the second one will be, if you do any microstructural analysis, or microscopic analysis of the samples that were heat treated, or all the samples, because I did something like that, and I want to see what what your answer is.
Normally, the up to 120, 140, you take only water. Of course, humidity plays a big role on the response of bio-based, all of them, because normally, if you have more water, you increase the formation capacity. So when you dry it better, and also you reduce the strength capacity. Your material become a bit more soft, because of the role of the water between the cellulosic materials of the constituent. So when we dry it, to use as reinforcement, we just kept the humidity of constant. So it was equilibrium humidity. So we didn't do thermal treatment to use the material as reinforcement in the bioconcrete. Okay, Hector, we just did the thermal treatment to see how the segment itself behaves under tension. So after that, we avoid it taking water back during the process, and then we test it in a thermohydral camera, keeping the humidity controlled inside, or dried, so this is the point. So and then what happens is that we start to the lignin has a big range of thermal degradation, so you start to degrade lignin very early, and it goes up to 300. So depending on the temperature, you are losing the bonding material between the filament, that is more cellulose and hemicellulose. I don't know if I got exactly if this was your point, but this is what we can.
Yeah, because I noticed the same on thermal treatments when, well, first when you raise the temperature, the material becomes more brittle, and then, yeah, of course you lose lignin, and so you start affecting the cells inside, so the cells
Yes.
start collapsing, and in
Yeah,
my
and the
case, I
cell
apply
bond.
some pressure, and the cell
Because
bond,
then,
yeah, the cell bond.
when the bundle it becomes many filaments a little bit loose, like if you lose capacity, then the fibrous cells start to break, and then you have a brittle failure, because the load that the number of cells is taking, if one break, that load needs to be supported by the rest, and then it is a progressive damage. It's like a telescopic failure that starts to happen.
Again, I do like the work that you've done, and I do like the next step that you mentioned, and is the LCA analysis, because that's, we had the same question, because you did show us how much post-treatment you need to do to the strip of bamboo to make sure that you have a good addition with concrete, because that's the problem, isn't it? With concrete, we have rebar that has a corrugated rebar that increases the friction with concrete.
Yeah.
So that's what you're doing with concrete. So in our result, really, in the result that we found was that it wasn't that environmentally friendly, really, to use round bamboo, to use bamboo in the round as reinforcement for concrete. So that's something that we said, no, don't do it. I do like that you are doing the processing, and I think, yeah, the next question is, let's look at the life cycle assessment, the carbon footprint of doing that and using that and replacing it, because many times people think that bamboo can be used as a replacement in a like by like situation with steel, and that is probably not the message. It's more, you need to look very deep into it. I don't know what you think of.
Yeah, the first thing is ordinary concrete. It has elastic modulus in the same range of bamboo 20. So it's not a good combination if you use. So it's very difficult to control the crack formation for ordinary concrete using bamboo, even if you improve the bonding, because of the material is already quite stiff. This case of bioconcrete is a very flexible material. It has elastic mold in the range of 5 to 6 giga if we use 25 to 30% of biomass inside. If we go to 6 to 7%, the elastic mold comes to 2 to 3 giga. So it keeps 8 to 10, the rate between the elastic mold of the reinforcement and of the matrix. Then it approaches the same rate as the structural concrete. So it's much better, the performance, when you go in that direction. So if we go to reinforce natural concrete, you should come to use lightweight aggregate. So you should bring the density of your material down to low down a bit the strength and the elastic mold. Then the behavior is much better. To solve the problem of life cycle assessment, we are using castor resin, so natural resin. We are testing now. Of course, it's not as good as the synthetic, and we need to improve it. But we got already half of the behavior. We got a bit more than half the behavior than we got with the epoxy resin. So yes, we should look for bioresins to improve the CO2 potential of the material.
Excellent. We are almost at the end. I think there is a question for Carlos also. So yeah, Juan Pablo.
Gracias, Héctor. Una pregunta para Carlos. Bueno, magnífica.
Thank you. This one is for Carlos. All three presentations have been fantastic. I'd like to congratulate you on your work and the analysis that this leads to, because this allows us to find more evidence to provide the authorities with, because they are the ones in charge of building. In this case, we have the Ministry of Housing. And of course, this can have an influence in their program. So in this case, construction with bamboo. This question is related or refers to the policy of having cultural housing policies. From your perspective, I haven't seen this document yet. It looks very, very interesting, but certainly you have analyzed this. So how can we make this document greater, have a higher coverage in Colombia? Because it maybe should not only focus in the coffee axis. We've seen other places, for example, the area of Caquetá, the area of Meta, and other areas also have bamboo and are starting construction processes. So we don't want these processes to be limited. There should be other incentives provided elsewhere. Is this an official document government? Is this a proposal? What have you seen from that perspective, Carlos? Oh, thank you, Pablo, for your input and for your question too. Let me clarify this. I've spoken about two documents, being the first one, a document called the Housing and Habitat Policy adopted by the other government, the prior government, that includes the concept of cultural housing. In the past, we only spoke about social housing that included different categories, but now this is the priority one that has better ranges, where the subsidy from the government is greater. Rural social housing has stopped since 2015 because it was in the hands of the Ministry of Agriculture. Now it's been given to the Housing Ministry. And in addition to this, it's important to mention that part of the work of the Housing Ministry was to create a public policy. And for this, there was an interaction with different regions. We had the chance of participating in roundtables. We even held a workshop. There was a poster of this. We did this with another university also in Pereira, however. And finally, this policy is applicable on a national level. So the one that includes these parameters is a national policy. We are lacking, however, an implementation for it. So with the change of command, well, the previous one was not able to increase it, and now the new one is trying to add new projects, and we hope that they will be able to have this ready very soon. The other document that is being fostered has been led by the Ministry of Agriculture. So this has been part of the work done from FEDEWADWA in order to have incidents in public policies, and this was supported by the Congress, by the Chamber of Representatives at a point. So this was done at the Senate, and there was support for this policy. And in order to avoid this being just a one-off, where there was just a register of this, we're able to include this paragraph, which is at this moment mandatory. Now, if you were to ask me when reading the paragraph refers to the cultural landscape of the coffee axis and the rest of the country and regions. So I don't know if this was intentional or not, but allegedly it should not be restricted to the coffee axis, but to the whole country. But there is a weird relationship to it. But yeah, it seems to have a greater scope. I believe that both points should be regulated, and perhaps this can be done with resolutions of each ministry, but we feel very optimistic because we believe it should not only be restricted to the coffee axis. And of course, I'm very happy to share with you the reason why, because I think that some of these issues can be handled in Ecuador, in Peru, and in the neighboring countries as well, in order to see what can be done or what could be some persuasive elements versus decision makers. Thank you very much, Carlos. I would like to give you the floor, Hector, in order to wrap up the meeting. Well, indeed, I would like to add something, but before this, I would like to invite all participants to turn on their cameras This is a long-lasting INBAR tradition where we take a group picture.
Turn on your cameras. We'll be taking a group photo with all the participants. Carlos, quería decirte, yo creo que para complementar lo que decía,
Carlos,
lo que te preguntaba Pablo.
let me add to the words of Pablo. I know that you will shortly publish something. Let's cross our fingers to have it ready whenever you present the results. And this is part of a process or an international methodology that could also be adopted in any other place of the world. So thanks everybody for your participation. Would like to thank you on behalf of INBAR. Would like to thank the three fantastic, great panelists, the three speakers that we had today. Would like to thank them for their presentations. And thankfully, this has led to many questions. We have your contact information. I'm sure a lot of people will get in touch. Thank you for your time. And thank you to all participants today. I would like to express my greetings.
Is a pleasure to share from the Latin American experience to all the world, all the work that we are doing. So thank you very much to participate. Kuwait, please.
Okay, thank you very much. Let's welcome all the participants to attend our next session next Tuesday. See you.
Okay,
Bye-bye.
for the picture, bye-bye. Salud para la foto, bye.
You got the picture.
Bye bye.
Bye-bye.
Thank
you.
Have a nice day.
Bye.
You
Have a
too.
good
You
night.
too. Have a nice night.
Good night.
Bye.
Bye.
Gracias a todos.
Valeu, família.